Okay, so we have a lot of information to cover, which is why I gave you, if you've seen the module, you will see that there's a packet of notes that you can take. They're kind of like fill in the blank notes. That way you're not writing everything. That's going to be better to use if you can print it off. Again, I put on there, if you can't print it off, email me and I'll make a copy for you. And if you can get to the school to pick it up, that's the only alternative to printing it off. I can print it off for you and then I can give you a copy of the notes packet. There's a lot of teachers that like drop them off up front, off the bus ramp, and so I'll give it there. With that, I'm going to try to go as fast as possible with the slides. You need to be able to pause the video and be able to fill in those blanks on your own, read the notes on your own. That's going to cover it, but I'm verbally going to cover the main points throughout the lecture. I'm not going to be able to cover everything in the slides because that's going to take forever. And so I'm going to try to go quick. So the first thing we're going to talk about is temperature. Again, the title of this section is temperature and thermometers. So temperature is just a measure of kind of how hot or cold something is. And that's what we really think day to day. But what it actually is, it's a measure of the sum of the kinetic energies of everything in the box or in the mass or the matter we're talking about. So on a microscopic scale, we have these atoms that are, if it's a gas, there's a bunch of atoms moving around. If it's a solid, all these atoms are in this, are a lot closer together. But either way, no matter what, atoms are moving. If they're solid, they're shaking, but if they're liquids and gases, they're moving around through space. And if you have motion, then you have this thing called kinetic energy, which we'll talk more about next semester. And so what temperature is the sum of all it's an average of the kinetic energies in a body. And so we're kind of figuring out like how shaky is my object. That's what temperature is really telling us. Okay, and temperature is always, it's transfer from one object to another, and so and not necessarily temperature, but heat, the actual heat and the actual energy within the object. It's always going to be transferred from hot to cold. It's always moving from hot to cold. It never automatically moves from cold to hot, although we can make it move from cold to hot if we do work, if we have some sort of other thing like some sort of engine, some sort of like refrigerator, AC. We can do some process that takes a lot of energy, but we can make it happen. But naturally, everything's going to always move from hot to cold. And again, temperature is just the sum of the kinetic energies, of the average kinetic energies of an object. And so if you heat an object up, things are going to get faster, which means that our temperature is going to go up because now the objects are moving around faster and moving around, bouncing around, and that means we have more kinetic energy. And so on average, we have a greater kinetic energy per atom, and so we're going to get a greater temperature. The thing we need some sort of reliable way to measure temperature. And so to develop that, we need to talk about two terms. We need to talk about thermal contact and thermal equilibrium. So thermal contact just means that two things of temperatures are in contact with each other. If they're the same temperature, nothing's going to happen. They're just going to stay the same temperature. But if you have two things that are different temperatures, heat is going to be transferred from them. And they're going to be transferred until they reach thermal equilibrium. We call thermal equilibrium when the two objects have the same temperature. And so they're going to keep transferring until they equalize. And this is essentially how a thermometer works. What we do is we put a thermometer of some sort of temperature into some chamber or into a liquid. If you're like cooking something, you're going to put it into whatever you're cooking, and they're going to equalize. That temperature is eventually going to reach the same temperature as whatever it's in, and it's going to read that temperature. And so this is the base of how thermometers work. We put something called mercury into a glass, and mercury is a liquid, and it expands a lot whenever it heats up or cools off. And so we can put in something hot, and it's going to expand. And as it expands, it's going to climb up. It's going to expand and get bigger, and we can read it on the scale we see here on the right. And if it cools off and it's just something cool, it's going to cool off, and it's going to get smaller, 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 and it's going to read something else on the scale. And so we can define things by just putting numbers on a scale. The most common thing we're going to use in this course is Celsius. Celsius is a scale. It's used basically everywhere else except for the US. You've probably heard this before. 0 is the freezing point of water. 100 point is defined as the boiling point of water, and the rest of the scale is based off those two numbers, which is a brilliant scale because water is our basis for most things. So that's why we use Celsius in science. That's why we use Celsius in most other countries. America has just got it backwards. They decided to use Fahrenheit for whatever reason, which I believe it actually does have certain useful uses to these numbers, but I don't remember them off the top of my head. They seem random. They seem like, why would I make the freezing point 32 and why would I make the boiling point 212? Who knows? And so those are our points in the Fahrenheit scale. And using those, you can actually, make a linear graph and you can create the equation yourself. We just need to be able to convert between them using this equation right here. You don't really need the other equation. It's just messed up on the slide. Don't worry about this. You need to know that the temperature in Fahrenheit is equal to 9/5 the temperature in Celsius plus 32. So if you want to get the Fahrenheit, all you gotta do is plug in the temperature in Celsius here and, simplify the equation, multiply your number by 9/2 and then add 32. If you're in Fahrenheit and you want to reach the Celsius temperature, did I turn off notifications? I did, okay. If you're in Celsius and you want the Fahrenheit, or you're in Fahrenheit, you want the Celsius, you just need to do the algebra. You need to plug in a number here and then solve for Celsius. Or I'm not going to show it, but you can Google the equation. There's an equation very similar to this one that you can solve for Celsius. And if you want to write that down in your notes, you can as well. There's also the third one, it's Kelvin. Again, you've probably heard this from either chemistry or, even middle school maybe. Kelvin is very similar to Celsius and Fahrenheit, except for we want all positive values. We don't really care for a negative value. We want 0 to be absolute 0. There is a minimum temperature things can be, because temperature is based off like the shakiness and the motion of atoms, right? But what if objects were completely still? And that's what absolute 0 is. If we can somehow get an object to be completely still so the atoms aren't moving at all, we would have the temperature absolute 0. And so that's what we base Kelvin off of. That limit, that point where we reach 0 Kelvin is when the atoms stop shaking completely. And so we have a conversion between Celsius and Kelvin. They're equal to each other. We just need to subtract 273.15 from the Kelvin. And let me make sure I'm thinking of that right. The Celsius version. Yes, okay, yeah, sorry. I was trying to do this on my head. Okay, yeah. So if you have the Kelvin number, then you want to subtract 273.15, and then you're going to get your Celsius number. And the reverse is true. If you want to get your Celsius number, all you need to do is add 270. If you want to get your Kelvin number, all you need to do is add 273.15, and you'll get your Kelvin number from Celsius. And so here are the main points that relate to each other. 32 and 0 and 273 Kelvin are all our melting points, and 212, 100, 373 are all of our boiling points of water. And on the right, you see what they're useful in. Fahrenheit is used in the US for meteorology and medicine. Celsius is basically used everywhere else for most things. And then when we get into like deep physics and chemistry and gas laws and stuff, that's when we're going to use Kelvin, because it's a much more useful idea for us. And then, yeah, you can see all this scale here, this picture. It shows all the scales and different things here. Thermal expansion. We're going to talk about this quickly. We're not going to do too much math on it today, I don't think. But you need to know the idea. As temperature increases in a gas, volume increases. Okay? If we keep the pressure the same. And so if we increase the temperature of a gas, we're going to increase the volume. And this is called thermal expansion. So, and this is why like things break outside. Sorry about all these notifications. This is why things break when you go outside, like these cracks in the brick. This brick, when it's put together, maybe it's put together on a really, really hot day, and so it's a little bit expanded. You don't really tell that solids expand, but they do. And when it's really hot, they expand a little bit. And so you build a house out of it, and you put everything together. And then all of a sudden winter comes. And what happens in winter? It gets cold. And now these bricks shrink. They don't shrink a ton. It's definitely measurable. If you went outside and took a ruler, you'd actually be able to measure the difference, but it's only like a couple millimeters maybe at most. So it's really insignificant. But when things are stuck together tightly like that, those millimeters matter, and they end up cracking the brick. And so that's why you end up cracking this, because it's contracting together and it's cracking it. And also the same thing with liquids and everything, in general, as you increase temperature, things increase, and as you decrease temperature, volume increases. The only difference is that water, it's hard to see on the slide for whatever this reason that point is showing, or that link is messed up. But it's saying that water is the exception. It's water, for whatever reason, it increases this volume as temperature decreases. And you can test this if you get a really, really full water bottle and put it in your fridge or into your freezer. It's going to expand, and it might break the water bottle if it's weak, but it's probably just going to push out the bottom and maybe push out the sides of the water bottle a little bit. Because as water is just weird, at least for liquids and solids, as it gets colder, it increases volume. Once it gets to a gas, then it goes the opposite again. Okay, so this next section we're going to cover is heat. We're going to define heat. So we need to define a couple other things first. We have this idea of internal energy. And so we talked about temperature was the average of all the kinetic energy. So all the shakiness of the atoms, that's a type of energy. It's called kinetic energy. And if we add up all the kinetic energies of an object, we get something called the internal energy. But not only the kinetic energies, but there's also potential energies in atoms, which is the potential for them to do stuff. And so it's just kind of a stored energy inside the atoms. If we add up all these things, we get something called the internal energy, and it's called U. That's the symbol for U. It's not the actual kinetic energy of the object. So if the object itself is moving, like if a car is moving on the highway like 50 miles per hour, that's not the kinetic energy we care about, but we do care about the individual atoms and their shakiness, okay? And so that's the energy we're talking about here. That's the internal energy, the inside of the box, not how the whole mass is moving on its own. And so if you heat up gold, it doesn't move, it's going to stay in the same place, but it's going to get more shaky. Those atoms are going to start moving a lot more. And so the internal energy is increasing. Same thing with ice. The actual volume of it, and the water's not really going anywhere. It's going to expand a little bit, but it's not really moving. It's not gaining velocity, but it's shaking. It's getting more internal energy. And then also, we can talk about a couple examples. So if we have 1 kilogram of water at 40 degrees Celsius, and then another mass at 20 degrees Celsius, obviously the one with the higher temperature has more shakiness. It has more kinetic energy, so it's going to have more internal energy to it. However, if we have two objects at the same temperature, or what does this say? Two samples of, for example, 10 grams of water at 0 degrees Celsius instant pressure and 10 degrees of ice at the same temperature and pressure. We're going to skip that slide. I'm not going to worry about it right now. Yeah. Sorry. I thought there was another slide in here. I guess I was wrong, so that threw me off. Okay, here we go. Here's the slide I was looking for. I think I just skipped it. The temperature is two samples of water are the same, but the first has twice as much mass. So we have one object that, maybe like 5 grams of water, and we have 10 grams of water. So one is twice as massive as the other. They have the same amount of shakiness, but one has twice as many atoms. And so it has twice as much as overall shakiness as the first one, right? Because it has twice as much atoms. So it's also going to have twice as much energy, even though the temperatures are the same. And so I want to get this idea out of your head that heat and temperature are the same thing. They're not. Heat is the amount of energy, and it has to do with the internal energy, while temperature is a measure of the average. Okay. We're going to skip this one. You can read it on your own if you'd like to. And so it turns out that the actual internal energy of a body, it's very hard to calculate. It's basically impossible. I mean, you would be basically measuring millions and millions of atoms, right? That sounds crazy complex. We can't really do that, but we can measure the change in internal energy of a body. And part of the way we do that is heat. So heat, as a definition, we talked about a little bit last class with those gizmos. Heat is the transfer of energy from a warmer body to a colder body. And so as temperature is changing in bodies, as heat is transferring from bodies, or we're letting energy go through. And this change of energy is called heat. And so Obviously, the greater the temperature difference, the two bodies, the greater the rate of energy transfer is going to be. So yeah, consider warm can placed in cold water. It's obviously going to cool down a lot faster. But as they start to equalize, that change is going to slow down. And it's measured, it says back here, it's measured in joules. It's a scalar quantity, so energy is scalar, so we don't have to do any vector work with this unit, which is nice. But there are some other units, and so we have one called calories. And so here's a list of them real quick. We have joules, which is our standard. This is what we're going to use for all of our problems, unless I say convert to calories or something. We have calorie. This is the lowercase c calorie. This is 4.186 joules. It's not really used that commonly. It's found in like older textbooks and stuff. It's not very that common. But what we do have is something called a kilocalorie, okay? So it's 1,000 of our normal calories. And it turns out that the calorie that you and I both know, when we talk about food and stuff, that's actually 1 kilocalorie. So 1 kilocalorie is equal to 1 capital C calorie. And so you'll see there on those two lines where it says kilocalorie and it says that the calorie with a capital C, or like calorie or dietary calorie, they have the same thing, right? They're both 4.186 times 10 to the 3 joules. And it's really stupid why they decided to do that. Like whatever scientist decided that, hey, let's call a kilocalorie also a calorie. It bugs me. I don't know why. It is confusing, but that's just the way it is. So a lowercase c calorie is 4.186 joules, and then a uppercase calorie is 1,000 times that. It's 1,000 calories. There's also something called the British thermal unit. I don't think we'll really use this unit. I don't plan to put it on anything. But there it is if it came up at all. But I don't plan to put it in anything. So again, energy transfer. In general, things are going to be transferred from the higher energy to the lower energy. But it can be direct. It can go in either direction, however, but because average kinetic energy of particles is higher in the object at a higher temperature, it's more energy is going to move out of the object into it. And so it's a weird way to explain it. Essentially, you need to understand that higher energy is going to move to lower energy. That's what's going to happen here. Sorry, 1 second. Okay, heat transfer. So again, there's different types of ways we can transfer heat. You probably heard of these before. We're going to go a little bit more in depth into them than you've probably seen before. So we have conduction. What is conduction? Conduction is the transfer of heat by the microscopic collisions of the particles of the movement of the electrons within a body. What the heck does that mean? Conduction means that it's kind of like bumper cars. These atoms are in direct contact with each other, and when one bumps another, it gives it energy. It transfers the energy through direct contact. You need to stop thinking in terms of like conduction as solids and convection as liquids and gases. To an extent, that's true, but to another extent, that's not always the case. That's not really what it means. Conduction just means that the atoms are in direct contact with each other and directly giving each other. Gases can also do this. If a gas molecule bumps another gas molecule, that is conduction. It is directly transferring energy through bumper cars, through hitting the atom, and it shakes it, and they start both vibrating and moving off together, and so there was conduction there. It's direct contact. Okay. It can be determined, as like an iron skillet. If you heat metal up, the ones directly in contact with the metal are going to start, the metal itself is going to start heating up, right, on the stove, and then it's going to start heating the pan. But it's going to start by the points direct contact with the pan. It's going to start shaking those, and then that pan is going to slowly diffuse out. The parts of the pan in direct contact are going to start shaking, and they're going to start shaking the parts next to it, and over time, the whole skillet is going to start getting heated and vibrating, and then once the skillet's heated, it's going to start heating the food on the plate because the food is in direct contact, so it's going to start vibrating those molecules and so on, and it's going to start getting heated. And the rate, it depends on the properties of the substance. We talked about this a little bit. Some metals and some substances conduct heat faster than others. We called it specific heat, and we'll study a little bit more. We'll have formal notes on it. I think maybe next class. I think it's next class. Well, the more formal notes on it. But metals just happen to heat up stuff fast, and so that's why we use them. They don't take a lot of energy to heat up. And so we have things called thermal conductors. These are things that heat things really well. So and general metals are good, although aluminum is an exception, which is why we like to wrap stuff in aluminum, because it's an insulator. It's a better insulator than most metals. And so we have also thermal insulators. Thermal insulators do not like to transfer heat very quickly. And so there's a list of them there: cork, ceramic, cardboard, glass, and all sorts of stuff. Fiberglass is one. That's why it's in your attic. You put fiberglass in your attic because it's a poor conductor of heat. It's an insulator of heat. It's going to keep heat out of your house, and it's going to save your electricity bill. Convection is another transfer of heat energy. It has to do with the movement of the molecules themselves. And so this is not going to occur in solids, which is why they kind of divide it up, like conduction is solids, because solids can only do conduction, okay? However, liquids and gases can do both conduction and convection. It involves the movement of the particles themselves. And so if you have a hot air balloon, okay, there's two things going on. That fire is heating the molecules right around it, okay? And then those air molecules that are heating around it, they start heating the layers above it. So they start heating the layer above it, and then the layer above it, and then the layer above it, and so on. Like a stack of, I don't know, think of floors of a building. The first floor gets heated, and the second floor gets heated, and so on. It's layer by layer by layer. That's conduction. Convection is the fact that the air itself, when it gets heated, it actually gets lighter because it expands, so it's less dense. And so that air does not just stay there, it moves. The hot air itself moves through the air into the hot air balloon and starts expanding it. And that's convection. The particles themselves are moving and causing the average temperature up there to be warmer because the warmer molecules are moving. Convection is the actual movement of the hotter molecules instead of the bumping of them. And so it mainly has to do with air. Liquids do this as well, though, but you can really think of gases and how this works. Radiation is the third way we transfer energy, although this is not going to involve matter at all. Thermal radiation is through light. So anytime you have light sources, it's going to transfer some sort of heat, although some are much stronger than others. And so this is where we think about the sun and we think about light sources. The sun is transferring heat through us, but the space is a vacuum. And so there's no way that it's like convection or conduction because there's no gas or liquids or solids in space to conduct heat. So it has to be through electromagnetic radiation. And so we send heat waves. So the sun is providing heat energy through rays, through radiation to the earth, and it heats up the earth. But it turns out, just because the sun is like visible and it's a very good one, that's not the only thing that gives off radiation. Turns out everything gives off radiation. Okay? I don't know if it shows this anywhere on here. So I'll let you do the slides on your own. All the PowerPoints are on the canvas. But I really just want to talk about that. Really, everything gives off some sort of radiation. Have you ever seen an infrared camera? If not, you should look it up. And you'll see that humans have some sort of infrared quality to them. You'll see like the hotter part of the human is, more red or whatever, and then the colder parts are more blue. It's meaning that we have some heat to us, and we actually give off radiation. We give off a certain amount of heat energy through radiation. Everything does. Everything that exists. Anything that's moving gives off some sort of radiation to it. And this is very important to us because otherwise the earth would just burn up. But the earth also gives off radiation, and that's why even though we keep gaining energy from the sun, we're also losing energy through space, and so the Earth is giving off some radiation so that we can cool off a little bit. Otherwise, we just burn up because keep gaining energy from the sun. And so here's a little picture. You can see conduction is the actual metal touching his thumb and touching the pot. That's conduction because the actual pan is starting heating itself up and it's directly touching the liquid, so that's conduction. Convection, you can see that it's boiling, and so some of the water at the bottom that's hotter is moving to the top of the water and starting to heat it up while the more dense water is moving down. And then there's radiation. That fire, it's heating only straight up, but if you sit next to a fire, you're also going to get heat, and it's because of the radiation from the fire. And so we have this idea of conservation of internal energy. If we have some sort of isolated system, we're going to keep energy, right? Energy it can't be created or destroyed. It has to only be transferred. But if we have an isolated system where energy is not going in or out, that means the total energy in the system has to stay the same. That's essentially what it's saying. It's just essentially a reiteration of the law of conservation of energy. We can increase internal energy by friction, but we're not going to really cover this because we don't really know how to do energy with friction yet, and so we don't really need to worry about this. But you do need to know that friction creates heat, essentially. So and you can do this, rub your hands real quick. You realize that your hands are going to warm up real quick as you rub your hands, and it's because friction is creating heat. The math behind this, we're not going to worry about this unit, so I wouldn't worry about too much. And so, yeah, these last few slides, you don't need to worry about. Even in your notes, you don't really need to fill them in because I'm not going to test on anything about this or even do homework on any of these last few slides. So with that, don't worry about these. You should be able to finish the homework. I think the homework for today is just, I think it's two things. I think there's a gizmo that I need you to do. It's on conduction and convection. It should be pretty straightforward. It's a little bit short of a gizmo. And then I think the other homework is thermometer stuff. So it's conversion between temperatures. And so, again, if you need to look up the conversions between both Fahrenheit and Celsius, and then also Celsius to Kelvin, and then you can Google them real quick if you want to and get more of them. I gave you the equations if you want to do the algebra for them, but there's a couple more equations you can use to shorten the algebra for you, make it easier on you. And just complete the worksheet. It shouldn't be too hard. With that, I am done.